Good afternoon, and thank you for joining us for the 61st webinar in the Offshore Wind Series, Learning from the Experts. I'm Kate McClellan-Press, Senior Project Manager with NYSERDA's Environmental Research Team, and it is my pleasure to be joined by today's expert, Travis Miles. Before I introduce our speaker, a few reminders for participants and some background on this webinar series. Next slide, please. Firstly, if you are experiencing any technical issues, please contact Ayla Morwin at the email address on the bottom of this slide. This webinar is being recorded, and the recordings and presentation slides for all webinars in the Learning from the Experts series are available on NYSERDA's website at the address on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Slido feature to submit your questions. Next slide, please. New York State is working to advance the responsible and cost-effective development of offshore wind as part of a diverse energy supply. Offshore wind is a critical component in achieving the state's energy reliability and decarbonization goals. While offshore wind has been providing clean energy to other parts of the world for several decades, this industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select Learning from the Experts speakers based on their expertise, not necessarily for an alignment of opinions with NYSERDA or the state of New York. Please note that the views and opinions expressed in this presentation are those of the presenter. Next slide, please. All right. It is now my pleasure to introduce Travis Miles. Travis is an associate professor in the Department of Marine and Coastal Sciences at Rutgers University in New Brunswick, where he also received his doctorate. As a co-director of the Rutgers University Center for Ocean Observing Leadership, he has pioneered the use of autonomous underwater vehicles and ocean observing networks to study the ocean's response to and feedback on hurricanes, coastal ocean processes, and investigating the interactions of offshore structures with coastal physics and ecosystems. I'm now going to hand things over to Travis. Thank you so much for being here with us today.
Great. It's going to go to the wrong slide, but I'll get us on track. There we go. All right. All good. All right. Well, thanks for having me. Yeah, I'm going to be talking kind of generally around oceanographic research and offshore wind, and with some specific projects that I've worked on here at Rutgers with many collaborators, which I'll show in a minute. So while I'm giving the talk, some of the slides I'm giving are from friends, coworkers, and other scientists that are really engaged on this topic. And first, I'd just like to acknowledge NYSERDA's support, New Jersey Department of Environmental Protection and Board of Public Utilities through the Research Monitoring Initiative, and just the generally Rutgers, the Center for Ocean Observing Leadership. So this has been a multi-state kind of effort and research that I'll be sharing some results on today. All right. Okay. So first, a little bit about where I'm coming from. So we've mentioned the Rutgers University Center for Ocean Observing Leadership. The acronym is Are You Cool? This is a little bit unique in universities in that we have a collection of, I think actually now 10 PIs, 10 scientists that are really coming together and running a laboratory that is really focused on experiential learning, bringing the ocean to our students in the classroom. This is the Cool Room, the Coastal Ocean Observing Lab, bringing the ocean to our students in real time and engaging them in oceanography, atmospheric sciences, and these real problems that impact people. So this is our group. Much of the results I'm going to be talking about are my own, as well as Josh Kohut, up here in the upper right, and then Grace Saba in the bottom middle. Those are kind of the three of us that are contributing to this talk today. A little bit of history. So Rutgers has a long history of working for the benefit of the people. It's a state land grant university, like many universities in New York as well. And it started out in 1862 as that land grant university. Its mission was to provide immersive hands-on research and experiential learning to build a sustainable and just future. A lot of its initial work started on agriculture, farming, things like that. But as early as 1901, we were working on shellfish. So this is out at Barnegat Bay. Things like the Clean Water Act came out of some of this early research and monitoring efforts that were happening back then. We have agents in all 21 counties of New Jersey. Those agents are full faculty and extension specialists who are really integrated into the community quite a lot. We also have a couple of marine field stations and this kind of merging coastal campus, which is actually 5 field stations kind of merged into one coastal campus. Which is aquaculture innovation, Haskin shellfish, and a few others. Are You Cool? We're on campus, so we're not in the coastal campus, but we're kind of this data and integrated campus node for the coastal campus, where we kind of connect into these different groups, both in the state of New Jersey and globally. So that's just a little bit about where I work. We'll go on from there. What I and we work on are kind of these core areas. We have some goals around protecting safety and life at sea, which is some of the work I do with hurricanes. We also operate what's called a high frequency radar network that helps with tracking. Basically, you can put in particles and track people. So we provide data directly into search and rescue operations in this area, and we operate that laboratory here. With our group, we study climate change all the way in the Antarctic and in the tropics, how heat moves across the planet. I spend a lot of time working on forecasting for hurricanes using underwater robotics, as well as working in coastal ecosystems. And then we also innovate and develop new technologies. So not just research technologies, but also like things like commercial fishing gear. For example, this one is around shellfish that Daphne Monroe works on, and how we might operate some of our fisheries in and around offshore wind turbines. And then our core goal is we're educators, so we're training the next generation in this kind of dynamic laboratory setting. All right. Today, the talk I'm going to give is a brief background on offshore wind. I'm going to give an overview, a very high-level overview of the physical oceanography of the Mid-Atlantic Bight, which I'm defining as the region basically from Cape Hatteras, North Carolina, to Cape Cod, Massachusetts. So that's all New York, New Jersey, everything in between. What and how our group and other groups measure and monitor this region, and some specific examples around offshore wind, and then some recent findings of dynamic ecosystems and interactions with offshore wind lease areas that we've been working on. But before I get into that, I just want to frame things. I'm pretty cold right now, despite how cold I am. I want to frame things a little bit around this, just kind of what the big challenge is. We've been talking about offshore wind for a while now, but reminding people that some of the issues that we're facing. So I pulled some of the data from the NOAA state climate summaries for New York. And this is temperature change relative to the 1901 to 60 period. And I just want to highlight that orange line. We are in some of our warmest average temperatures, despite how cold it is outside today. You see a lot of bouncing around in this line. And it's projected that that's going to continue to increase. Even under low emission or high CO2 emission scenarios, we're going to continue to experience increasing atmospheric temperatures. So keeping that in mind when we think about renewable energy, but also the research that we're doing on the ocean that is experiencing that change as well. And then instead of just temperature, I also wanted to highlight water levels, issues we need to face around sea level rise, flooding from things like extreme hurricanes, or even just rainy day flooding or tidal flooding, are projected to continue to increase as well. We've seen increases, so orange is the observations since the 1920s. We've continued to see more basically flooding days per year up in the last few decades. And there's projections showing that to continue to increase. And this is at the Battery in New York. So we just need to keep these things in mind when we talk about developing offshore renewables and mitigating some CO2 and climate. So I like to frame that up. I also, as we talk a little bit about offshore wind, I want us to keep in mind where we're getting our power from, where we're getting our electricity from. This is, a little out of date. It's from 2019. But this is for the entire US, kind of generally where our mix of electricity comes from. And you can see basically we've seen some drops in coal. So it used to be 51% of our power production. Now it's down to 23. That's largely been replaced by natural gas. We see nuclear looks like it's staying constant, about 19%, but I think after 2019, we've actually seen some drop-offs from shuttering of plants. We've seen some increases in wind, some kind of consistent mix coming from hydroelectric, and then a few other solars down here. Now, this is the whole US. If we focus in a little more, this is just for New Jersey, which is similar to New York. There's some differences, but just for New Jersey, you can see that renewables is a really relatively small percentage, this yellow. We have natural gas, which is still high. We have nuclear, which is still high. We don't really get a lot from these other sources. So mainly it's nuclear, natural gas, and then renewable energy that are the three things we're thinking about. In New Jersey, our targets for offshore wind renewables are still hold for 2030 at 11 gigawatts. With everything happening nationally, we may not hit that, but those goals are still the ones laid out for New Jersey. And that's relatively speaking what those goals, this yellow bar I added on, is how much that this yellow would expand if we hit those goals. So just to keep that in mind when we're thinking about this. Now, those developments are not happening in a vacuum. They're not being proposed in a vacuum. We've all heard kind of over the last few years around some of the challenges here. But generally, 24 lease areas have been proposed. Roughly 3,500 turbines in this region have been proposed. And you can see the lease areas back here, also layers of ship traffic and other things kind of showing some of the shared uses. And I think I crossed this out because I personally don't know what the federal goal is anymore, so I crossed that out for now. But there are still lease areas moving forward. There are still developments moving forward. There's some that are already built. So it's not, offshore wind is a thing that's here and that we need to research and study. This region also has a lot of shared uses. So it's the third largest U.S. port. It's $210 billion in value, in container value, like 15,000 vessels a year. That's what all those lines moving through this area are. 18% of the U.S. population is in this region. So about 19 million people in New York, New Jersey, and PA, and more if you kind of expand it out to the whole mid-Atlantic. We have about over 5 billion in commercial and recreational fisheries. And then for New Jersey, we're really focused on this. Shellfish alone generated about 500 million in fishery landings in the region. So there's a lot of shared uses and pressures kind of on this region that are beyond offshore wind. So with that in mind, there's some advantages, opportunities. Offshore wind turbines, they don't occupy land resources, which are also in short supply. One thing is they could also be built larger than on land. Some of that's around permitting. But there's also a much larger, more reliable wind resource offshore. So the winds go up significantly the further offshore you get relative to on land. And basically, when they're larger and you have more wind, you get more power per turbine, which means a lower cost per megawatt. So offshore wind was really those things aligning were allowing prices to kind of come down and match closer to some of what the conventional sources of energy are. There are many challenges, though. the one I have highlighted is the one I'm going to talk about today a little bit. We have a very dynamic physical, biological, and ecological environment, the ocean characteristics of our region, which I'll get into. There's multiple ocean uses, fisheries, recreation, shipping, national security. There's new regulatory pathways and supply chains that need to be set up, and there's a lot of evolving legal permitting and policy landscape. So there's a lot of challenges. We're setting up this new industry in the US, and I'm just going to talk a little more about that first one today. We've written a few review papers on this. I'm happy to kind of share these afterward, or they'll be shared in the slides. So we've written a few review papers on how wind farms could influence continental shelf oceanography, alter ecological processes. I've written two of those review papers. We've looked, there's been a few consensus study reports on how hydrodynamics might affect specifically North Atlantic right whale has been a concern in and around Nantucket. That's a critically endangered species. I think there's between 300 and 400 individuals left, and like 60% of that population is in and around the Mid-Atlantic region on a regular basis. So there's been a few review papers on that that we've contributed to that have also framed some of our research. So just keeping that in mind as I go. So these are the very high level processes of the Mid-Atlantic bight. So what I have here, you can see the coast of New Jersey, New York, and this whole region. Layered in the background is just an image of the sea surface temperature. So this is temperature. I believe this looks like winter temperature. So you have these cold nearshore waters in the winter. And then you have this warm offshore water. This is the Gulf Stream that's actually going to the north. So this is water coming from the tropics, very warm. We have water coming from the poles in the Arctic over here. And then we have a lot of variability in between. You also notice a lot of kind of what are called eddies, meanders, and fronts, a lot of details. These features change on the orders of days to weeks. This is a really difficult thing to study and understand. A lot of nonlinear physics here that we have a difficult time predicting, but a lot of variability here across shore. We also have freshwater inputs at the coast, so freshwater river output from the Hudson and Raritan Bay, Long Island Sound, Delaware, Chesapeake, and so on, all putting water and associated properties into this region. We also have a very large seasonal stratification, which I'll show later on in a minute. Basically, seasonally, we get really warm temperatures in summer and really cold in winter, and that sets up some interesting stratification. Where we get storms, we get hurricanes, we get winter storms. So it's a really, really dynamic region. The feature I'm going to focus in the most on is called the cold pool. So I'm going to explain some of the stratification that we get in the region. This is not a new feature. This feature was kind of first measured in 1933 from some of the light ships. So this is the Sandy Hook light ship. You can actually go and eat on, I think it's the Frying Pan Shoals, but on the Hudson, there is a light ship that's been converted into a restaurant. These are old, instead of lighthouses, they were ships that were moored. They had lights on the top, but they would also do oceanographic measurements periodically. And some of those early measurements back in the 1930s showed this, these temperature features. So this is all temperature data. And I highlighted in blue the 10 degrees Celsius, what's called an isotherm. And basically what this is showing is this kind of coherent feature. Each of these transects corresponds to one of these lines. You have A here, B for some reason is at the top, so that's the middle, and then C is at the bottom. But all of them show this coherent cold kind of blob feature that is known as the cold pool. So these were some of the first measurements reported on that. And I'll get a little more into that. Here is a paper from the 1979 showing kind of the spatial footprint of that cold pool. Again, that 10 degrees Celsius, and this is a top-down view of the bottom temperatures. So temperatures at the bottom. You can see in March, kind of in spring, you don't really have it. So basically, that cold water is, or that kind of cold pool feature is the whole shelf. It's basically 10 degrees C and cooler inshore. Similarly, in May, you still don't quite see it. You're warming up a little bit. And then here is where in July you see this bottom temperature really defined. So there's this cold mass of water. So in July, when it's warmest at the sea surface, we still have these cold waters at the bottom. And then that starts to kind of recede as you go into August, September, and October. I'll show this again a couple more times, so don't worry if these perspectives aren't great. So this was the 1970s. When we start looking at it kind of from a side view, so this is data from what's called an underwater glider or a robot, which I'll talk about in more detail, but if later on. But if we look at this side view of a transect, basically like one of these transects across the continental shelf, you can see the cold pool forming in time. So in October, we have these temperatures at of about 15 degrees Celsius here at the surface. We enter into winter. It's cold top to bottom. So this is around 5 degrees Celsius or lower. March, still really cold. And then into June, into summer, we basically superheat the surface of the water. We heat it up so fast that it doesn't heat the entire water column. It actually just forms this thin, warm layer at the surface. And then in August, July, August, that really sets up. So we have really, really warm water here at the surface, but we've kind of trapped this cold water mass at the bottom called the cold pool. And then you cycle back into the next October and it gets mixed away. So what happens here is that we set this up through seasonal stratification, warming from the sun, and then storms basically come through and mix that water up into the surface and turn it back into this uniform water mass. So something I don't talk about today, but Hurricane Sandy and Hurricane Irene back in 2011 and 2012 were things that we looked at. And this cold water mass actually mixed up to the surface in Hurricane Irene, cooled the surface of the ocean, and weakened that storm before it made landfall. Sandy actually pushed it offshore and didn't actually weaken Sandy. So Sandy came in strong because this cold pool was basically gone. I could give a whole nother talk on that topic. But what's really important about this cold feature for our ecosystems is that it actually extends the southerly range of commercial and recreational fisheries. So fisheries, fish that normally live in cold water or might be found in like the Gulf of Maine or things like that, they can actually make their way further south and stick around in summer, make their way all the way down to Cape Hatteras, where this cold water is. A lot of fish basically form their life history based on the seasonality of this feature. A lot of like shellfish will time their spawning and kind of larval behavior around this cold water mass in the region, which supports some of that really large scallop fishery. So basically, this is the water mass that they're living in. Also, as far as ecosystems, the water can be upwelled at the coast to drive local phytoplankton primary productivity. So that cold water is usually really nutrient rich, brings those nutrients to the surface, and you can grow phytoplankton blooms. Some of you might have experienced this. I know at the Jersey Shore, if you go to the shore on a really hot day in summer, and the wind is blowing kind of from the south, you may think, hey, I'm really hot. I'm going to go in the water, cool off. Well, you might get really cold. Sometimes in Fahrenheit, I think you can get around 60, 50 degree water, 60 degree water, even when it's, 90 degrees in air. And that's actually that cold bottom water upwelling at the coastline, and you're in the cold pool. And then I kind of already mentioned this buffer for hurricanes. Now, I've presented this as kind of this static water mass by season, but if we look in a little more detail, so this is ocean model data, and what I'm showing here is a kind of 3D view of a 12 degrees C isotherm. So again, this is kind of like a layer map of the cold pool throughout a year, and you're going to see it moves around quite a lot. So this isn't just This is June. This isn't just a feature that comes and sits there. It starts to move back and forth, and that's due to that offshore um, Gulf Stream meanders and variability, but also just winds. Our winds can actually move this feature around and cause it to change and evolve. So there's a lot of variability in even one given year around the cold pool and its behavior. I think I'm good on time. Just play that one more time. So here you can see May. It's got its June. It's got its kind of biggest area. It starts to shrink kind of from the south and the north, July, and then you get storms that come through starting really in August, September, October. Nor'easters will come through, and they'll start to mix this away. And then those cold temperatures just keep it cold. And it's mostly gone. Okay. Now, some questions now coming back to offshore wind that we've started to look at is, okay, this cold pool features here, there could be some interactions with offshore wind turbines and the foundations and monopiles having impacts on the cold pool itself. So our first question we asked was just how much overlap is there between this cold pool feature seasonally or by month with the actual proposed lease areas? And so my PhD student, Becca Horowitz, looked at some of these maps from about a decade of ocean model data and looked at overlaps between the lease areas and the cold pool. And there's two numbers we looked at, which is the wind lease area overlap. So how much of the wind lease areas were covered by the cold pool? And then the next number is how much of the cold pool in total was in a wind lease area. And so what you can see is kind of April, we have this 19 to 10%. It peaks in May. So almost all wind lease areas have overlap with the cold pool, about 81%. The ones off Virginia don't have overlap here because the cold pool is a little bit more to the north. And then 13% of the cold pool is over a wind lease area. And then that starts to go down. So 62%, 41%. 18%, and then it basically no overlap because the cold pool's gone starting in September, October. So there is significant overlap, especially in this stratified kind of May, June, July period. And those are time periods where we really want to understand how the cold pool and turbine foundations interact and what that means for ecosystems. So this is kind of where we framed it up. We have an evolving plan around offshore wind development. We've talked about some of the dynamic environment. And then there's also this dynamic ecology, so layered onto that. So these are kind of the three areas where we need to understand what's going on to understand any potential impacts or changes that we might experience from turbines and ecosystems, but also we need to understand how that environment is changing on a climate scale as well. So not just impacts from turbines, but how do we balance that with impacts from climate? So it's kind of the framework for where we're thinking right now. So I'm going to focus on, there's kind of two areas we're focusing on and that were identified in some of those earlier review papers, that we need to establish a baseline to assess impacts from ongoing climate change, but also offshore wind development. So that baseline is really important. We need to collect data to understand the state of our ecosystems and the state of our physical ocean. And then we need data to perform some simple modeling experiments to gut check our more complex systems. So this is kind of two areas I'm going to talk about today. Now, how do we do this? In Are You Cool, one of the core technologies we use is called a Slocum glider. This was basically a science fiction article back in 1989 by Henry Stommel. Well, he got together. He was a physical oceanographer. He got together with an engineer, and they dreamt up this idea of a robot that could basically roam our regional ocean, and that was where the Slocum glider came from. This was first deployed in 1999 at the Rutgers University Marine Field Station, and the first mission was done in 2003. So I'll tell you a little bit about what it is. So this is in Tuckerton, New Jersey. Here we have basically the cutaway of one of our Slocum glider underwater robots. what you can see is that the front is basically there's a buoyancy pump. You have a brains of the glider in the back, this control board, and then the most important part is you have this science payload in the center with some sensors. And then the second most important part is that that data gets off the system every time it comes to the surface in Iridium satellite phone. So communications is back here. So we have science, communications, and then we basically have these robots roaming the oceans, which I'll show a quick video of. So here is basically they use buoyancy. So they'll suck in a little bit of water in the nose. They'll shift a buoyancy system, and they'll dive through the water column. They have a rudder to basically dead reckon with a simple compass. When they get to the bottom, they'll push that water back out, become lighter than the surrounding water, and they'll come back up to the surface. And then they'll do that over and over again. When they finish their a couple of dives, they'll come to the surface, they'll send their data back to shore. And then we ingest that data. We look at it right away. So actually we get data every about 3 hours from every one of these systems that we put out. And we ingest that data into our models. It collects data every 2 seconds from standard sensors, and that's about 20,000 samples per day. So this is a lot of data per platform, but you can think of them like weather balloons for the ocean. Let's see. Let's click through. We've deployed these all over the world. So we did that first deployment back in 2003. Now we've done over 600 deployments. This is a few probably from last year's statistics. So I think we're closer to 700 now. We've gone about 8 times around the Earth in the amount of space we've sampled, and about 50 years worth of data that we've collected from multiple platforms being deployed. These red dots are just where Rutgers has deployed gliders. SUNY Stony Brook also works with us in the region and is a big partner. And there's a lot of people internationally that are starting to deploy them, including in Antarctica. We're doing some of that, but all over the world. That data goes into NOAA, National Weather Service, and then that gets sent into operational forecast models. So it's not just data that scientists look at, it's actually supporting operations in real time. And then we use it in data products, but also kind of ecosystem monitoring, which we'll talk about in a minute. Now, some of the advantages of glider-based monitoring is you don't need a ship, so it's basically cost effective. A ship can cost something like $40,000 a day to go out on a large research vessel. A glider costs about $40,000 maybe a month to run. So we get a month's worth of data versus a day's worth of data. It's very high resolution. So this is like the scatter plot of data from a short couple of days with depth on the y-axis and time on the x-axis. And I believe this was chlorophyll here. But it can be out in things like hurricanes and hazardous conditions. And actually, we have a lot of experience now navigating within wind farms with these systems and collecting data in and around lease areas. Sensors that we can integrate into that science bay, they're standard. Some of the standard ones here in blue: temperature and salinity, physics and ecosystems, dissolved oxygen, which is fisheries and water quality. And then we can get into things like pH, ocean acidification, and the carbonate system. We can also look at chlorophyll and optical backscatter. And then we started to get in more around active acoustics, where we can look at fish, zooplankton, marine mammals. We can actually do passive acoustics for marine mammal detection, which I'll talk about in a minute. So a lot of these sensors can be co-located on a single glider, and then we have multiple gliders roving around collecting that data. Okay, so kind of the first science update I'm going to give you on where we're at. One of our core questions, this was from New Jersey DEP, is with our glider data in a simple model, can we estimate what impact offshore wind turbine monopiles might have on the mid-Atlantic bight? And so the theory here is basically that when you get flow, so this is flow, don't worry about the equations too much. When you get velocity and flow and currents moving past a structure, you can have wakes and turbulence generated, and that can mix things like the cold pool. So here's the simple schematic of that. We wanted to study whether that was actually something we expected to happen here in the mid-Atlantic. And to do that, we wanted to look at some simple models. Um, I think mostly ignore this. I won't have any tests on equations other than these red parts. What we're getting at is that this is a water velocity cubed as part of these equations, and that means if a little change in velocity, so a little speed up of a current, can have a big change in ocean mixing. And then also there's components of stratification that are included. So stratification is like your ability to resist mixing, and then velocity cubed is your ability to overcome that stratification. So we need to kind of understand these two things and balance out to get an estimate of how much mixing might happen from something like a turbine. No quiz on this, don't worry. So no problem there. So generally, we have a simple model we came up with. We need data to set up that model. We've gotten that from our gliders, from those decades of glider data that we've collected in the region. Here's data we've extracted from just a single New Jersey lease area. We've used that data to kind of develop some sort of average expected cold pool profile of the water column. And then we run our simple model. And we run it a lot to try to come up with estimates of how much mixing we might have. And we compare that with the currents of actual velocities in the region. So this is a beast of a graph, and I'll try to go in detail maybe in the question and answer section. But basically, what we're seeing here is these green are the number of days of actual current speeds we observe, the velocities we observe in our region. And these are timescales that current would have to actually have to fully overturn the water column. And the thing to highlight here is there's basically a big gap between due to monopiles alone. There's a big gap between the velocities that actually occur and then what would be needed to fully overturn the water column due to just turbine monopiles, not things like storms and other natural variability, but just monopiles. If we summarize this in kind of one take-home message here at the top, is that for turbine monopiles alone, just monopiles, to add mixing and impact the cold pool, it would take about 30 years of flow past those turbines at a typical velocity that we get in the mid-Atlantic bight to overturn the water column. So we really don't think that's reasonable. We don't think from our back the envelope estimates that turbine foundations are going to fully kind of destroy the cold pool or mix it away. That's not something we expect. The caveat is that we do expect smaller amounts of mixing that might affect things instead of like erosion of the cold pool, nutrients. They might affect phytoplankton or zooplankton aggregation. So those questions are still out there. I know that's a quick summary of some complicated physics, but I want to get to a few other things. So I'm going to highlight two other projects kind of as I start to wrap up. One is the project Glide. This was supported by NYSERDA for myself and Dr. Kohut and Leslie Thorne at Stony Brook. And these are glider-based ecological and oceanographic surveys of the region, and then also the Eco Glider project for NJDP for Grace Saba and Kohut. They have similar goals, and it's collecting this baseline hydrographic data and ecosystem data to understand things like phytoplankton, everything from phytoplankton marine mammals. On the right is all of the data that we've collected in kind of this area with some highlighted. These are highlighted EcoGlider missions. There's been 81 of them with this special suite of sensors. So the first one I'm going to talk about is marine mammal surveys. So we actually have passive acoustics on our gliders. These can basically are hydrophones that are listening for things like marine mammal calls. And when they hear those, they actually process that data. And they can classify what type of whale or marine mammal they heard, and where it was, where they heard it, and kind of they'll come to the surface and send that little snippet of audio back. This is in partnership with Woods Hole Oceanographic Institute. The robots for whales at hui.edu, you can go and see if we have any systems out listening for whales. You can go and see us and partners where gliders are at, what they're hearing in real time. So for this particular day on the left, this is a couple of right whale detections, two right whale detections from a ocean glider off the New Jersey coast. We recently have a paper kind of aggregating 5 years of data of doing these surveys and having some kind of basic findings. So this was from Katie Gallagher at SUNY Stony Brook. And basically what we're finding, the plot on the right is detection days per kilometer surveyed. So this is kind of like how much detections we're getting from our robots. And we looked at this seasonally. So for example, in winter, we're getting most of our detections of, this is particularly right whales, actually. Most of our detections in winter are more near shore in these kind of in the New Jersey area right here. We're seeing that's where most of our detections are. That doesn't mean we're seeing a lot of them. That's just where most of them are happening. Um, in spring, we see those kind of shift more offshore. So we have less in this nearshore zone and more detections offshore outside of wind lease areas. And then in summer, we have the least detections in the lease areas and in general, and everything's kind of shifted offshore. So we have questions about what they're responding to. Is it the cold pool? Is it their food source around zooplankton? You know, what is happening in the ecosystem that those right whales are kind of moving and responding to? And that is still an open question. So collecting this data and follow-on studies to try to understand what they're making choices about is something we're working on. So we have a little baseline data there. And then lastly, I just want to highlight, I kind of got at this before, but some of the baseline monitoring that we're doing off New Jersey for RMI, for the DEP, the main thing we're able to start to see is this seasonal evolution, but then also large seasonal variability in these things that aren't just temperature and salinity, but also looking at like chlorophyll and oxygen and pH. And so, for example, here, this is 1 year of 4 deployments in 1 year, and you can see the data beneath this transect here. You can see setup of stratification early on in this springtime. You can see some features around low dissolved oxygen and pH, which could be an issue for our ecosystem. You can see things like a hurricane came through and mixed the water column and temperature. You can see here in early fall an overturn. So suddenly now we went from summer conditions into fall conditions. And then you can see winter conditions over here. And then we can pair chlorophyll or pH variables along with that. I don't go into detail of findings on this, but I just want to keep that in mind, what we're able to see within a season. And then also we're starting to see things interannually. So here are some model data results of bottom temperature, but also the supporting glider data that went into that here on the top. And some things that we're seeing from just a few years of data is that we can see a large variability in temperature from year to year. So this is summer 2023, and you can see temperature anomaly. So basically temperatures are a few degrees warmer above average on the inshore edge here, colder offshore. And then in summer of 2024, we see a much colder continental shelf region. So summer 2024 was remarkably cold for reasons we're still researching and trying to publish on. And then there's corresponding changes in the properties that we see, like oxygen in the bottom water. So you can see big differences in the oxygen concentrations in these two areas, with lower oxygen in 2023. I think I changed that. Yeah, it's wrong. Lower oxygen in 2023 than in 2024. Which has some issues for fish, lobster, and crab mortalities. And a lot of this is mostly independent in offshore wind development. You know, we're looking at data off New Jersey where we haven't actually had any turbines constructed. So this is just giving you a flavor of kind of interannual variability we can see. And so I'm thinking as we go forward, when we have construction happening, you know, there's this background variability that's just kind of natural and happening, and we need to keep in mind. I'm going to start to wrap up there. So generally, we're all unsure about the long and short-term future of offshore wind on the East Coast. Turbines are being built. We don't know how many or how fast, based on kind of policy right now. The cold pool is our signature oceanographic feature that we need to understand that supports fisheries and ecosystems. Generally, we don't expect turbines to kind of mix or destroy the cold pool, but we need to understand nuances of how they might impact, aggregations of zooplankton, food for marine mammals, things like that. We need to continue to monitor these parameters to have more robust estimates of kind of long-term change. And generally, I just want people to know we have the technology to do this and have been doing it for years. But it's just hard work and we need more data. So thank you for the support, and hopefully we can keep doing this and come back with new results every year as we go. So with that, I will thank you all. Thank you to our lab and the funders, and thanks for the invitation to share some of this today. So I'm happy to take questions and take the slides down. All
Thanks
right.
so much, Travis. And yeah, so if you have a question, we have plenty of time for Q&A. So please use Slido to enter your questions. And that was a great presentation and lots of stuff to think about and lots of great questions coming in. And wonder if one thing you could talk about, and you described really well in your presentation, is the offshore is such a dynamic environment, and you're measuring lots of different things at the same time. How are you able to try and figure out like the cause of change, like offshore wind versus all of the other things that are dynamically happening in the environment?
Yeah, it's a really challenging problem, and I think most of what I focused on today is our data collection. But I think we really need models. So I think like the data is really good for validation and calibration of modeling systems, and those modeling systems are what we really need to do experiments and ask questions and try to understand, how all these pieces add up. So when I'm talking about modeling systems, I'm mainly talking about physical models that can represent features like the cold pool and their mixing and things like that. But our models are only good as the data we put into them. So we kind of need to merge this approach of collecting a lot of data with ecosystem parameters, testing, doing experiments and testing things with models, and putting those together and getting them at the right scale so we can actually answer questions and do experiments like changing the number of turbines that are in that model, or changing the drag coefficients, so I think that's ultimately the place we need to be. And I think we're just really early on in having the data that we need to answer, kind of pose even those questions correctly. So we've had some amazing data sets now to do that.
Yeah, and you're partnering with lots of different other disciplines and working in fisheries and marine mammals to try to couple those types of data. Are there any other, like the glider can detect a lot of different things? Is there anything in addition to kind of what you talked about that it can also do? What are some of the kind of like long-term measurements that it's taking? How long can it stay out there? What other things are you detecting, or would you like to be able to detect?
Yeah, I mean, I think we're the ones I highlighted today, are great. I think some challenges are that, when we get a marine mammal detection, it's hard to know, was that whale right next to the glider? Was it 10 kilometers away? Was it the same whale? So I think there's kind of rather than needing more parameters, I think it's needing more platforms to kind of disentangle some of these things. If you have more systems listening to the same thing, you can triangulate locations and things like that. So that's kind of a complex thing. I didn't share too much, but we have other types of sensors on ocean physics to really understand the details of like mixing. We have things called like microstructure turbulence sensors, or ADCPs that measure velocity. And so there's other parameters in that space. And then we'd love to get eDNA sampling going. So there's kind of more biogeochemistry sensors that can tell you what, I mean, some of them could go probably as far as saying, oh, a whale passed through here over the last 5 days or something like that in the future. The technology is not quite there yet, but I think that's ideas. And you can do that with like bacteria and phytoplankton and zooplankton. And so I think that's the next generation of sensors that we're looking at. The gliders we're deploying, they can stay out for, about a month to 3 months, depending on the batteries and the sensors. And so we have pretty good duration out there, but we just need more kind of platforms to get out there to kind of cover the area.
Great. We have a couple questions about modeling.
Yeah.
One of them is a question around if any of these changes in dynamics from wind turbines, if they could actually impact kind of like the coastal landscape as well as kind of the offshore environment.
Yeah, it's a good question. I think from the ocean side, I wouldn't expect the monopiles themselves, like the actual kind of sticks in the water, to do too much in that space. I mean, there's a few researchers that are working on kind of, do you change wave propagation around, like, as waves move through these features, how do they propagate? Um, but I think the bigger question is probably on the atmospheric side. Like, you have these huge, huge blades moving, and how do the wakes from those blades affect the atmosphere? We've done a little research on that, and there's been a few papers showing most of the wake impacts are kind of are contained to the lease areas. That doesn't mean they don't have an impact on the underlying ocean. But I think there are scenarios where you might have wind blowing from a particular direction and that wake goes over land. And I think that's a really interesting area of research on whether that's, a good or bad, what does that actually impact? I would say I'd largely be more like the New Jersey lease areas that are pretty close. Well, I mean, they're close-ish to New Jersey. If the prevailing winds were from a particular direction, what would that impact? I think that's still a research question that is out there. And but I would also caution that I think anything that's talking about these studies need to be paired with how is climate change in general impacting some of those same things like agriculture or coastal weather. And I think those things need to be looked at kind of in balance. We may have impact, if we don't have renewable energy, and we're going to have impacts anyway from just general climate change. So
Yeah, it's hard to, again, disentangle those
yeah.
those different things. You actually answered a couple of other questions while you were answering that, because we had some questions about how, that scale of impact on the atmospheric side, but also you kind of briefly mentioned, the history of wind in Europe, and the question is, how has that influenced the research in the U.S.,
Yeah.
particularly on the oceanography side?
Yeah, it's actually been really helpful. We have some great collaborators from Europe who've been working on understanding offshore winds impacts on physics and ecosystems. They got basically a decade or two head start on us. So one of our closest collaborators actually built that simple model I showed. And in Europe, some of the physical modeling showed that things like tides would basically mix the water column really quickly. And in Europe, tidal velocities are a lot faster. In the German Bight and North Sea, you actually get currents that are moving past turbines like half a meter to a meter per second, whereas here we're more like 10 centimeters per second. So it actually added a lot of there was some built infrastructure for us to bring over, some like modeling and conceptual infrastructure for us to bring over and work with, and then adapt to our own conditions. So it's been really useful. And I think what we're doing here in the Mid-Atlantic is also going to have knock-on effects on the way we do research in other parts of the world around, Asia is developing offshore wind research plans and development plans, and kind of the tools we're showing are having feedbacks more broadly. So I think it's a great test bed for the technology and the modeling here as well for the future.
Yeah, that's great. We have one question, just for you to go into a little bit more detail on the slide that you showed, looking at that 30-year
Yeah.
impact of mixing, and can you maybe go into a little bit more detail about your findings there?
Yeah, I know I highlighted that pretty quickly with a few equations. So for that project, we were really trying to get an back of the envelope, like order of magnitude estimate of how turbines might affect offshore wind or the cold pool, And like, do we need to invest a lot of effort in much more detailed, complicated modeling or not? And I think our goal was to basically come up with an estimate of how long from just turbines, just turbine foundations, not even the spinning part, but just the foundations, how long would it take flow past those features that we expect in the mid-Atlantic to impact the cold pool, to basically get rid of the cold pool? Because at the time when we started that, there were these kind of claims coming out of like turbines are going to destroy the cold pool, and we're like, I don't know, like I don't think so, but let's test it. Um, and so when we did that study, what we were left with was these time scales of mixing. And the model basically says, if you put this flow past the turbine for this long based on this stratification, this is how long it would take. And that's kind of what those numbers were. For a tidal velocity, it would take 30 years. For like a storm, for like storm mixing, it would take like 6 to 10 days, which is, scary. We're at 10 days. But the velocities at that storm speed, when we looked for evidence of how often those velocities have occurred, it was like hours. It was like Hurricane Sandy had really fast velocities for like 2 hours. And it's like, okay, well, that's still really different than winds blowing for hurricane force winds for 10 days straight. So we're trying to get a context of where the risks are. And I think from that paper, which is, I think we've already written a report and it should be submitted for review soon, for peer review. We're kind of seeing that it's not, they don't match up. Whereas in Europe, those timescales really match up a lot closer and it's a bigger issue. So yeah, that kind of gets at the question before around what we learned and how we adapted and what's different about our system as well, though. That's to say turbines might change patterns of zooplankton, which is prey for right whales. We don't need to destroy the cold pool to have an impact and change behavior. So that's still an open area of research.
Yeah, and I think that's one that there's a lot of new oceanographic research that is kicking off across the region too. So there's more to come in the future. I just have maybe one more brief question before we wrap up. And like the data that you're collecting has some of it has been driven by questions around offshore wind, but it seems like it is informing potentially a lot of other different industries or information. Who else do you kind of partner with to use this data?
Yeah, no data set goes unused. We're picking the bones of that data. We're picking every little bit of meat off the bones. So any system that we put out to study something like an ecosystem or marine mammals has temperature and salinity data that we send to the National Weather Service. That data gets ingested into operational models for real-time weather forecasts. So every single platform we put out there is collecting data for that purpose. Similarly, there's a lot of reasons to understand our fisheries and marine mammal habitats outside of offshore wind. So, even areas where turbines aren't being built or aren't going to be built, understanding the patterns of these ecosystems is going to help us understand our commercial fishery, our recreational fishery, our endangered species, and we're working very closely with people like NOAA, National Marine Fisheries groups, collaborative groups around marine mammal detection. And also, DP has been really interested in this, and also in New York, DEC funds a lot of Stony Brook as well for just water quality monitoring. I mean, understanding coastal water quality, oxygen, hypoxia events, things like that. So all the data is supporting those different efforts, and it gets integrated across these different groups. So, yeah.
Thank you so much for sharing, Travis. This was really informative, and I think we're going to bring up our closing slide. Thanks, everyone, for joining us today for this Learning from the Experts webinar. Just a reminder that the webinar recording and presentation slides will be available on NYSERDA's website. Our next webinar in the series will be on March 25th. Presenters from Ventilines will review timelines, sequencing, and key logistical considerations for construction and installation of offshore components of offshore wind projects. You can register for future webinars through our events page at win.ny.gov. We also encourage you to check out our past webinars in the series on NYSERDA's YouTube channel. And if you would like to request a topic or speaker for the series, please email us at offshorewind@nyserda.ny.gov or fill out our Learning from the Experts survey posted on our events page. Again, thank you for joining us today and see you next time.